Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe.
Lecture 8, Optimization. So, this lecture is going to cover one of the main reasons that people take calculus in the first place. There are a lot of application problems in engineering and the sciences and business that calculus can play a real role in solving. And so we're going to take a look at some general and, frankly, easy optimization problems. I can't cover the full spectrum of all possible optimization problems that you may ever encounter because they're everywhere, right? From electrical systems to engineering to finance related. But I'll do a few different types so you get a flavor of what they're about. And then in the homework set, problem set, there'll be some more problems to try that will increase the diversity of problems even more. But one thing that I should say from the outset is that the calculus in these problems tends not to be too hard. Okay, like in the last section when we maximized and minimized, where we were graphing, right, sketching graphs based on maxima and minima and concavity and things like that, and inflection points. Those were some pretty tough functions that you found in the problem sets. The ones you'll find here won't be, I think, nearly as complicated. What's going to be hard about these problems, however, is setting them up in the first place. Okay, so kind of a general theme that you're going to find here is you're going to have some general formula you want to optimize. Maybe it's the area or the volume of something. And then you're going to have to use geometry and drawings to try and find a second equation to get rid of all but one independent variable. And then we can optimize. Okay? So let's start with a kind of a straightforward problem. Let's imagine that we are an advertising agency and we're going to put out a little brochure. And it needs to contain some text. And we've calculated that the total area of text that needs to be included in this advertisement is, say, 50 square inches. So we have 50 square inches of text we need to display. And it's required that they have 2-inch margins on the left and the right and 1-inch margins on the top and the bottom. Okay, and so we're supposed to find the way to use the least amount of paper in displaying this advertisement. So the first thing that we should do is draw a picture. So like I said, I'm just going to assume that the area of the text, I'll just write it as inches squared, 50 square inches of text that we need to display, and we're going to assume that it's going to be displayed in a rectangle of some kind. So this would not include certain printing geometries where we had, say, maybe a circular print, right? That's something you could do, I suppose. But we'll assume that we're doing rectangular graphics, I guess you'd call it. And to the left and the right of this, we need 2 inches margins. This is terrible, 2 inches margins. And at the top and the bottom, we'll have a 1-inch margin. Now, I haven't solved the problem. I've drawn it in a very particular way. It may turn out to be that the printed text is going to be taller than it is wide. But we just need to get some picture so that we can start to lay out some variables here. And so we can say that, the width of this print, we'll call that x, and the vertical portion of it we'll call y, and that the area in the end will be x times y. And this is what we're going to try and minimize. We want to minimize the area. So because, the more, if you can minimize the amount of paper you use, it lowers cost, right? Yes. So that's the idea here. So we now have to introduce the constraint in this case. We have this 50 square inches. Well, 50 would be equal to what? That's the size of the text inside here. So we can look at this and we can say, well, that's going to be x minus 4. X minus 4. And the vertical portion of it is going to be y minus 2. Everyone sees why that follows, right? Yeah? So it was from the picture that we drew that we were able to write this second equation. Now, we can use this constraint to eliminate one of these independent variables, x or y, in the area formula. And so if I solve this, let's say for y, so we'll end up having x as our only independent variable, then we would get that y is going to be equal to 2 plus 50 divided by x minus 4. And so we can then rewrite the area as x times 2 plus 50 over x minus 4, which we could expand and where we could distribute that x, and we have 2x plus 50x divided by x minus 4. Now, what do we need to do now? We have a formula for the area. It's written only in terms of a single independent variable, x. So if we want to optimize it, that means we want to find either a maximum or a minimum. So we need to look for critical numbers, yes?
Yeah.
So how do we find critical numbers?
By taking the derivative and solving for x.
Well, we need to take the derivative of the area with respect to x and set that equal to 0. That will give us our critical numbers, or look for any place where it's not defined. But before we do that, let's just take a look at what the domain of this problem is. Can x be any value? Could x, for example, be 0? Well, I think that you can convince yourself pretty quickly that the domain of this problem is such that x is greater than 4 and, well, we'll just say less than infinity. Let's just proceed with the optimization portion of this. So we need to find the derivative of a with respect to x. And so I'll ask you at home to pause the video and try taking that derivative now. Come back when you have your answer. dA dx. We'll differentiate this right here term by term. The first term will have its derivative is 2. And then for the second term, you see that we have a product rule here. A quotient rule that we need to use. So we'll get x minus 4 times the derivative of the top, which will be, say, 50, and the derivative of x is just 1, minus the top, 50x, times the derivative of the bottom, which is just 1, all divided by x minus 4 squared. And so distributing the 50 through this term x minus 4 here, we'll get 2 plus 50x minus, well, 50 times 4 is 200, and then minus 50x, all divided by x minus 4 squared. 50x and 50x go away, and so we're left with 2 minus 200 over x minus 4 squared. And we want to set this equal to 0, which means that we would like to make this equal to 0. So we can say that this is equal to this, which is the same thing as saying that 2 times x minus 4 squared equals 200. We can divide both sides by 2, turning this into 100. Take a square root, and that gives us that x is equal to 4 plus or minus 10, because the square root of 100 is 10. So 4 minus 10 is a negative number. We can see that that's not in our domain, so we can exclude the minus term here, and we would only consider the positive term, so we get that x is equal to 14. And we're not done yet, because we don't know if that's a maximum or a minimum, do we? So if we were to take a second derivative, let's just summarize our results up here. So we have so far critical number x equals 14. We can go ahead and take a derivative of this d2a over dx squared. Derivative of this would just be 0, plus we'll have the minus 200 times minus 2 over x minus 4, this time cubed. So that's going to simplify to positive 400 over x minus 4 cubed. And so for any values of x in our domain, in particular for x equals 14, 14 minus 4 is just 10. And so we have 400 over 10 cubed, which is a positive number, which makes that concave up or down?
So that would be...
It's positive, it's positive. It's concave up. positive values for the second derivative imply concave up. If it's concave up, that means minimum. Okay? So that means that we have found our minimum at x equals 14. What about y? Well, we have an equation for y right here. So x equals 14 is the minimum value. What is the y value for that? So we have to plug that into this. So we get that the y value associated with this critical number is 2 plus 50 divided by 14 minus 4 is 10. And so that is 2 plus 5 equals 7. So the dimensions, the optimal dimensions for this advertisement are the x is equal to 14 and the y is equal to 7. Now it might benefit you to try some other values for x and y and see how much different the area is. You can do that. But let's go ahead and move on and let's try another type of optimization problem. Is it familiar with, have you ever heard of a 2x4? It's a piece of lumber. It's a piece of wood, so it's 2 inches wide by 4 inches tall. Yes?
Yeah.
So the strength in that board, if you were to try to bend it, right, you would want to have the 4 inches in the vertical direction so that as you bent it, right, there was more wood to resist. You can kind of see that, right? So it turns out that the strength of a beam of wood is proportional to the width times the square of the depth. Now, where the depth, that's the dimension that we're going to be doing the bending in, right? That's the important one. The strength of a beam is proportional to the width times the depth squared. Now, our optimization problem that we're going to be interested in is one in which we cut a beam from a circular log, okay? So notice that this distance here, let's say the log is of radius a. This dimension we'll call the depth. This one we'll call the width. Does that make sense?
Yeah.
Yeah. And so we want to optimize for the strength. We want to cut from this circular log. We want to choose the dimensions for W and D such that it optimizes the strength of the beam that we cut from it.
Yeah.
So again, we've got a picture here, and we have the formula that we're going to use that we're going to optimize, but we have 2 independent variables here, yes? We have the width and the depth already. So we need to find another relationship to eliminate one of these independent variables. So the Pythagorean theorem says that d squared plus w squared is equal to a squared. So we can solve for, say, d squared, and then substitute into the formula for the strength. Instead of putting d squared, we'll replace it with a squared minus w squared. So now we've only got one independent variable. A is fixed. It is a constant. Okay, we're not allowing a to vary. Yes?
Yeah.
So I can, of course, distribute the w, and we'll get a squared w minus w cubed. So what can we say about the domain of the problem? W would have to be greater than, could be greater than or equal to 0, but less than or equal to a. A, which is the diameter of the wood that we're cutting it from, would be the maximum width that we could attain, yes?
Yeah.
So we need to optimize this, which means we need to find the critical numbers for the strength. And again, I'm going to invite you at home to pause the video, try taking that derivative, come back when you have your answer. ds dw. We'll do this term by term. Give me a squared minus 3w squared. And so we're interested in, when is this equal to 0? Well, that is when a squared is equal to 3w squared. We can divide out the 3 on both sides, take a square root, and so we get that w is equal to a over the square root of 3. Now, is that a maximum or a minimum? Well, we need to take a second derivative to determine that. So we'll take d to s dw squared That would give us 0 for the first term, minus 6w. And so we'll try it out for w equals a over the square root of 3. And you can see that when evaluating it at that point, it's still going to be negative, right? Because of the negative number here. When the second derivative is negative, that means that this is concave down, which makes it a maximum. So the critical number w equals a over the square root of 3 is a maximum. But we were asked to find the dimensions that optimize the strength of the beam, and we've only yet found the one dimension for the width. We can get the depth from this formula here, the Pythagorean theorem. It says the depth squared will be equal to a squared minus the width squared, but the width is a over the square root of 3, so that's going to be a squared over 3. This is the same thing as a squared times 1 minus 1/3, but that's really just 3/3 minus 1/3, which is 2/3, which means that d is equal to the square root of 2 over 3 times a. And so we can fill this in. This will be a over the square root of 3, and this will be the square root of 2/3 times a. And those would be the optimum dimensions for that beam, to optimize for strength anyways. Now in the homework, I'm going to put in a problem that asks, instead of optimizing for the strength, to optimize for the minimization of waste. And so you'll see that you'll get a very different answer if you want to minimize the amount of waste in cutting a beam from a circular log than when you optimize for strength. Okay? I was going to do that in class, but I thought, no, it's a good exercise. It's not that hard to do. And so I left that for the homework. But let me show you a different kind of optimization problem. This is not so much application specific as it is more geometrical in nature. And so we're going to talk about trying to inscribe shapes inside of other shapes. And so I want to find the dimensions of the largest cylinder that can be inscribed in a given right circular cone. So we need to draw a picture of a right circular cone. There. So the right circular cone has a radius for the base of radius b, we'll say. The altitude of the cone, we'll call that a for altitude. The radius of the cylinder that we're putting inside of it we'll call r. The height of the cylinder we'll call h. That means that this distance here will be a minus h. I think we have all the relevant geometry in there. And then, of course, the volume for does anyone know the volume for a cylinder? You may have to look up when you're doing your homework some of these volume formulas. But I think I'll probably give in the problem the relevant formulas that you'll need. But the formula for the volume of a cylinder is pi r squared h. It's like you take the area of a circle and you multiply it times its height, right? Because that's kind of what a cylinder is, a stack of circles, yes? But now, of course, we need, how are we going to get that formula that allows us to eliminate one of these independent variables, r or h? And in this case, the easiest, I think, is to use similar triangles, right? So if we look at, say, the big triangle of height a over b is the same as the little triangle up here at the top of height a minus h over r. Does everyone see that?
Yeah.
So I could try and draw it in, let's do it this way. Let's draw it in red. The little triangle that we're talking about is right here. And so we could write this as a minus h over r, whereas a over b is the black triangle that you would draw going from here out to here. Yes? But they're similar. So this allows us to solve for r or h. Solving this for h, we get that h is equal to a minus a over b times r. And so we can substitute that into our volume formula to eliminate h. Distributing. And so now we have the volume expressed in terms of a single independent variable and then some constants, a, b, and pi. So go ahead and pause the video now, take the derivative of the volume with respect to r, and find the critical numbers. Okay, so dv dr, first term will give us 2 pi a times r. The second term will give us 3 pi a over b r squared. I would recommend factoring. I can get a 2, or I can get a pi, an a, and an r out of this. Pi a r, that leaves behind a 2 minus 3 r over b. Is that right? And so when this is equal to 0, or if this is equal to 0, that's two possibilities. Either pi a r is equal to 0, so we're getting some critical numbers now. R could be equal to 0, or 2 minus 3r over b is equal to 0, which means that r is equal to 2/3 b. So it's another critical number. So let's go ahead and take the second derivative now and see if we can find out whether these critical numbers are maxima or minima, because we're looking to maximize the volume of the cylinder we can inscribe inside this right circular cone. So we're looking for a maximum. And we probably have a good intuition as to which one's going to be a maximum, which is going to be a min, but let's just go through the motions. d2v over dr squared is going to be 2 pi a minus 6 pi a over b r. And so if we were to plug in r equals 0 into this, we get left with the 2 pi a. A is a positive quantity, so that would be a positive value. That would make it concave up, which means a minimum. So r equals 0 is not the one we're interested in, because that corresponds to a minimum. Then we could try r equals 2/3 b. And so plugging 2/3 b in for r, we're going to get 2 pi a minus 6 pi a over b, 2/3 b. The b's cancel. Let's say the 3 and the 6 cancel, gives us a 2 here. Let's factor out a 2 and a pi and an a. Leaves us with 1 minus, we would be left with a 2. Yeah, 1 minus 2, and so this is a negative number. And so that means that we have a concave down. And so that makes this, in fact, a maximum. And so r equals 2/3 b is our maximum value. Let's now figure out what h needs to be. So using the auxiliary formula that we use to eliminate the one of the independent variables with, we get that h is equal to a minus a over b, and r will replace with 2/3 b. B's will cancel, and so we are left with a times 1 minus 2/3. That's 3/3 minus 2/3, so that's just 1/3, so that is just a over 3. So r equals 2/3 b, and h is equal to a over 3. And so we can now replace this with a over 3 for the height, and then r we choose to be 2/3 b. And that would give us the largest cylinder that we could inscribe inside the right circular cone. So the last example I want to do is one from physics. I think it's a good result, and I think you may be able to use the result that I show here, perhaps in a problem in the homework. So I'm going to start by just simply drawing a picture. This is going to be a derivation of Snell's law. Okay, so this is to model what light does at an interface. Okay, so it's coming from, on the left here, the light is propagating from point A, which we're going to locate at x equals 0. So we have our coordinate system would look like this, where this is the origin. This is of height A. So x equals 0, y equals A, to a point, which we're just going to generically call a distance x away from the origin, to a point B, which is a distance, we'll call this distance here B, such that this would be B minus x, and also at minus c. So it's minus c in the y direction. Now, in the first, on the left-hand side, in material 1, we could call it, the light travels at speed v sub 1. But once it enters this material on the right, at this interface line here, it's traveling at a different speed, v2. Okay, so Snell's law says, if we define the angle of incidence as the angle with respect to the normal here, and the angle of refraction as the angle with respect to this normal, then Snell's law says that the sine of theta 1 divided by v1 is equal to the sine of theta 2 divided by v2. And so this is what we want to prove. And so you're thinking, why is this an optimization problem? Because this is really, it's in the way to understand this as an optimization problem is to know of something called Fermat's principle of least time. And so he reasoned that light always takes the path that allows it to travel for the least amount of time. So it gets there the fastest, you see? And so this would be very similar to a problem that you might encounter if you had, like, say, this is a lifeguard, this is a person drowning in the ocean. They run faster on the beach, but swim slower in the ocean. Find the optimum path to get to the drowning swimmer in the shortest amount of time. It's the same problem, except in this case, we're talking about light. Light wants to go from this point A to this point B. What path does it take that gets it there in the least amount of time? And that's what these kind of problems are. So we have to think, well, what is it that it's traveling? Well, we've got this distance L1 it's going to travel, and then L2, right? First, it's going to travel along here. That's length L1. What is that length L1? L1 is just going to be a squared plus x squared, right? It's just the Pythagorean theorem again. L2, what does that look like? Well, L2 is just equal to b minus x squared plus minus c squared, which would just be c squared. Yeah. But also remember, right, this is a principle of least time, so we want to minimize the time. So the time that something takes, remember that time is equal to distance divided by velocity, or speed. So what we want to do is we'll take these distance formulas and divide by the velocities. So we could write T1 is just L1 over V1. That's the speed that the light travels in that material, in this medium, yes? So that's a squared plus x squared over V1. And T2, this arm here in the second material, is the b minus x squared plus c squared divided by V2. And the total time is T1 plus T2. And we want to minimize the total time. But those are two separate terms, and so I'm going to choose to do them separately when differentiating them. So I want to look at dt1 dx. I forgot to take a square root. Distance. Yeah, sorry about that. This would be true of the distance squared, but not the distance itself. So these all need to have square roots on them. So now I need to take the square root. So the derivative of square root, of course, gives me a 1/2. Then we'll get the a squared plus x squared will be to the minus 1/2. Then the derivative of the inside will give me 2x using the chain rule. And all of this will be divided by v1. And so this will simplify to the 2's will cancel. I'll get x over the square root of a squared plus x squared. And of course, we have the v1 down here as well. But let's look at that. X over the square root of a squared plus x squared. That's this term here, right? And you can see that by definition, right, the sine of theta 1, which we've defined, is just x over the square root of a squared plus x squared, right, by definition. And so we get sine theta 1 over v1. Doing the same thing for d2 dx, we get, again, a 1/2 b minus x squared plus c squared, so b to the minus 1/2. And the inside of this, we'll get a 2b minus x, and then a minus x, minus 1, sorry, for the inside, all divided by v2. And so this will simplify to minus b minus x over v2 times the square root of b minus x squared plus c squared. I think that's it, right? Minus the 2's went away, got the b, yes, I think that's it. And so that is equal to minus, well, b minus x, that's this arm here, over the hypotenuse, which is the square root of b minus x squared plus c squared. That is just the sine of theta 2, or theta r as we call it here. Sine of theta r, but still divided by v2. And so now this plus this equals 0. Well, when does that happen? When this plus this equals 0 means that this equals this, yes? And so that is where we get, I call this incidence, fraction v2. That is the condition under which we would get the critical number. Now, as it turns out, it's not always the least amount of time. Well, actually, I think for time it usually is. I think it's when action comes into play that it sometimes can be maximum, just some extremum in the action. But for time, I think it's always going to be a minimum. We could investigate that by looking at the second derivative, but that's something that maybe you can do at home on your own time. But as you can see, we've derived Snell's law by optimizing the time traveled from point A to point B for light traveling at speed v1 in material 1 and v2 in material 2. And this condition, right, is just a condition for what the critical number is, right? I think that's all I wanted to say about that. But those are some of the applications that you can get for optimization using the tools of calculus. A little under the weather today, so slightly off my game here. Apologize for that. But work through the problem set. I think you'll learn a lot trying to solve these problems. And I think that they're good fun. If you like puzzles and problems like this, then this can be a lot of fun. The calculus will be the least of your worries, I think. The hardest part of this will be reasoning through how you're going to find a solution. Okay. But, you know, again, always start by drawing a picture, right? And then you need to find that auxiliary equation which will allow you to eliminate all but one independent variable in the equation, in the formula that you want to optimize. So if you're optimizing for the volume and, you know, maybe it's you've got x, y, and z in it, you need to get rid of y and z and just have it in terms of x. So you need to find some way to get rid of those two independent variables, y and z. All right, yeah, any questions? Okay, sounds like no. Then I'll see you next time.